When harmless cells suddenly gain new powers, biology becomes a crime scene. In Biology 110, we've studied cells, DNA, enzymes, and even how life copies itself, but nothing prepared me for what happened in the lab last week. A harmless, gentle strand of E. coli suddenly gained new abilities. It survived antibiotics. It grew where no cell should grow, and it wasn't an accident. Today, I open a new case file, the case of the transformed bacteria. These are our suspects: DNA, the genetic mastermind; plasmid, the accomplice; and the E. coli, the unwitting host. Every crime has its suspects, and in biology, our suspects are molecules. Suspect number 1, DNA, wanted for encoding every trait a cell could ever have. The motive? It wants to be copied, shared, and sometimes even stolen. Suspect number 2, the plasmid PUC19. Its known aliases are circular DNA, small but mighty, and the carrier of the ampicillin resistance. The motive? Spread its genes far and wide. Suspect number 3, the competent cells, the E. coli. Normally harmless, slightly gullible, but walls weakened on purpose. They don't really have a motive. They just accept whatever DNA wanders in their way. These 3 suspects are the core of today's investigation, a process called bacterial transformation. It's how bacteria gains new traits. It's like glowing, digesting new sugars, or resisting antibiotics. It's simple on paper, but in the lab, it feels like you're watching evolution happen in fast forward. Case file 1928, Griffith's experiments. Our case actually began almost a century ago, in 1928, when Dr. Frederick Griffith noticed something strange. A harmless, rough strain of pneumonia suddenly transformed into a deadly, smooth strain. It was only after meeting heat that it killed the smooth bacteria. It was impossible at the time, but some transforming principle, moved from the dead bacteria into the living. That was the first recorded case of DNA acting like a biological criminal, slipping traits from one cell to another. Griffith didn't know it was DNA, but today we do. And in our Bio 110 lab, we recreated this transformation with the modern suspects. In the DKU lab, we set the stage. First, we made our E. coli cells competent, weakening their cells so the DNA could sneak in. Then came the heat shock, 42 degrees Celsius for exactly 45 seconds. A biological smash and grab. This is the moment the plasmid PUC19 that carried the ampicillin resistance slipped inside the cells. When the cells recovered, we planted them onto an LB agar containing ampicillin. Ampicillin is deadly, unless you have the gene to survive it. On LB alone, all the cells grew. There's no crime there. But on the ampicillin plates, only the transformed bacteria survived. That was our evidence. The cells had really changed. They had new DNA, new traits, new abilities. The transformation was complete. The case had been confirmed. But transformation isn't just a classroom phenomenon. Out there, it changes the world, sometimes for the better, sometimes for the worse. Antibiotic resistance, if you take it, bacteria will pick up resistant genes naturally. This is most seen in hospitals, where this creates superbugs that we struggle to treat. It's also seen in biotechnology, where we use transformation to manufacture insulin, produce enzymes, and create biofuels, and design new medicines. Genetic engineering also has this. CRISPR often starts with a simple transformation step, inserting guide RNA or Cas9 into cells. In short, transformation is both a superpower, and a threat, depending on who wields it. Case closed for now, but the transformation will never truly end. Bacteria will evolve, DNA will move, and biology will keep rewriting itself. This was CSI, DKU, the case of the transformed bacteria. I'd like to say a special thank you to everyone who supported my Biology 110 journey. Stay curious and stay vigilant.